All right, Mrs. V here. We're going to talk about today about graphing, density, and experimental error. If you haven't already, please go into our Google Classroom and find your density graphing experimental error notes assignment and open up that Google Docs to take your notes. I am fine with if you want to take your notes on a piece of paper, but when you are done, you are going to have to transfer it to this Google Doc to turn in. I will not accept pictures, videos of anything of notes on paper. You will need to transfer it here so that I can see it clearly. If you send me pictures of it or video, I will just return it to you and tell you to put it onto this Google Doc. Okay? All right, so let's get started. So graphing, density, experimental error. I'm going to pull on a lot of prior knowledge from you guys. So try to remember what you learned in Math 1. Try to remember what you learned in biology. Try to remember what you learned in 7th and 8th grade science, even in elementary science. So a lot of this stuff you've had a couple times, and so you might remember learning it. Okay, so our essential questions today is what is density and experimental error, and how do I represent data on a graph? So you should be able to answer hopefully this question. If not, right after the notes, maybe after you process them, and we're going to use it in a couple labs this week. So variables, those are very important as we're graphing. There's a couple variables that we definitely use. The first one is independent variables. It is represented on the x-axis, and it is a variable that you choose to change as the experiment. So in biology, I use the example of different amounts of sunlight. Does it affect plant growth? Well, I can't change a plant's growth. I can't take a plant and stretch it out, make it taller, but I can change how much sunlight it has by moving it in different places. So the amount of sunlight would definitely be my independent variable, and that would be my x-axis. Then you have your dependent variable, and it's represented on the y-axis. And it is a variable being measured in your experiment. So in the plant example, it would be the height of the plant. I can measure that, and that would be on my y-axis or my vertical axis. Remember, your x-axis is your horizontal one, and your y is your vertical. So in this example, I'm going to have you answer a couple questions. So you decide to measure male children at different age in centimeters to see what the male growth rate is. So what is your independent variable? Is this your x or y? And what is your dependent variable? So I want you to go ahead and pause the video for a minute and try to answer those questions. So pause now. Okay, well, hopefully you had some time to kind of think about it. What would be that independent variable? What can I change? So you can change the age and years of male children. So I can choose different ages of children to measure. And so that would be my x, and the dependent would be what am I measuring? Height in centimeters. So that would be my y. All right, another important thing about graphing is labels and spacing. So labels are very important. You need, number one, a title of graph. You need a clearly defined x-axis, it's an independent variable, and y-axis, dependent, and you must include your units. That is very important. I'll show you an example of why it's hard to understand when you don't in a minute. Spacing, it should be based on your data. So you should be taking your data and deciding how you want it spaced. You should not be spacing them with the numbers you have. Oh, I have a 1, and then I have a 3, and then I have a 10. So that's what my numbers are going to be. Doing that, going up by 2 and then 7, so 1 to 3 and 3 to 10, is going to cause your data not to look right when you actually graph it. So you won't be able to tell if it's a straight line, curved line, maybe a parabola. You won't be able to see that if you don't have the correct spacing. So correct spacing is really important too. I use the formula every time I need to know how I'm going to space it. I take my high number, and then I subtract my low number, which is usually 0. Sometimes it might not be. Maybe sometimes I'm starting at everything at a certain thing, but most of the time I start at 0. And I'm going to divide the number of lines available. So here's my example. My high number is 160 centimeters. Say my tallest child is 160 centimeters. My low is 0. I'll set that 0, and I have 10 lines. So I would take 160 minus 0 and divide it by 10, which would tell me it would be 16, which means each line is worth 16 centimeters higher. So the first one would be 0, and then I would go to 16 and then 32. Okay? So here's an example of a very well spaced and labeled graph. So we have average height of male children, tells me what they're doing. I have height in centimeters, so this tells me these numbers are centimeters, and age in years. So I know these aren't months or whatever else they want to do. I know these are years. So then you also notice it starts at 0, and this starts at 0. So both of them start at 0, and then it goes up by 20s, 20, 40, 60. And by doing that, I can get a clear picture of what this line looks like. So I can see in the first few years, maybe 2 years or so, they grow quite rapidly, very quickly, very steep slope to a much more gradual increase. But they increase over time. All right, and also by doing the spacing, you can better get these best fit lines or trend lines. So here's an example. This is a pretty easy best fit line or trend line to get, but we have a fitted line and we see a straight line. So I can say, yeah, this one's a little this way, and maybe this one's a little this down here, but this is pretty much the trend that goes through most of them right through the center. They don't fit perfectly, but this is my best fit line so that I can see how this data lines up. And this one, it says true value, and notice they didn't give me the best labels here either. So it's kind of hard. So sometimes I have to think through, what does this mean? Well, true value, book price, but I can see there's a positive slope or increase. As we go up in book price, we also go up in true value, whatever that means. So that's why labels are kind of important. Here's another best fit line. This has a little bit more, so you can see they're kind of all over the place. And I don't want to connect here and then here and then here and here and here. I'm not going to see what the trend or what the overall picture kind of is. And so I find these middle lines, and I know you guys have all done this in math. And you find these best fit lines that goes through here. And this tells me, okay, I've got a positive slope. I definitely have an increase in weight over age. Now notice, I don't know if this is years or months. I have no idea. And I have no idea if this is pounds or kilograms. So, and I have no title. So this really doesn't give me a whole lot of information, except I can see that it has a positive slope. So whatever they're measuring definitely increase. They both increase at the same time. And I'll use my vocabulary, they are directly proportional. As one increases, the other increases. Okay? All right, another concept that you guys started in math is rate of change, and we're going to use that. So the slope tells me how something changes compared to something else. And if you remember, slope is rise over run, and it's y2 minus y1 over x2 minus x1. So that is how we find the rate of change and how maybe something is. So this is a slope, this is a graph of something that kind of gives me change. And this is distance versus time, and it's very nicely labeled here for a frictionless glider on an air track. So this tells me exactly that it's talking about a frictionless glider on an air track. And we're looking at how far it goes based on its time. So it's so nicely labeled. Look at time, it's in seconds, and distance is in meters. So you can see they did a nice best fit line through the middle. Some of them went straight through, but most of them are just off a little bit. But then they figured out the slope. So the change in distance, so they picked some things here, 60 minus 30 over 20 minus 10. And then they figured out this right here gives me rate of change, or how fast that glider went. What's the average speed of the glider on a frictionless track? And it is 3 meters per second. So they can use that in their advertising and their selling. So slope we use a lot here in science, and you're going to use it actually in some of your density labs. Okay. All right. The second concept I kind of want to get you to understand is experimental error. This is used to determine how well a scientist performed an experiment. Not only that, but how reliable their data is. So you will never have to understand like how you will never have, I guess you'll never have to memorize, what I'm trying to say is you never have to memorize this equation. I will always give this to you. But percent error calculation is the difference between approximate or measured value and an exact or known value. That means it's been repeated so many times, and we'll use this with density, that this is what we pretty much use as a whole in the science community as what this number should be. And it's calculated by percent error equals whatever value you measured minus our known one, usually from a book or a table, and you're going to take the absolute value, so that's always positive, and that's why we do that. Divided by the known and times 100. This will get you a percentage, and we like these experimental errors 5% or less. We call this the 95% confidence error, which means that the scientist is pretty much 95% confident that this experiment was really good. So this, if we have a higher than 5%, then a lot of times the scientists will redo their experiment to see if something affected it. And if they publish it, then a lot of times the rest of us wouldn't really pay too much attention to the results. We'd look more at one maybe that had a lower experimental error. Okay. All right, here's our last concept for today. We're going to talk about density. Density is the relationship of a substance of mass and how much space it takes up in our volume. So density talks about mass. Mass and weight are two very different things. Weight is dependent on gravity. So your weight here on Earth is very different than your weight up on the moon. But your mass here on Earth is the same as your mass if you were standing on the moon. Mass is about how much space you take up, how much things are in your body. So that does not change when you go to the moon, okay? Because it doesn't depend on gravity. So one of the things we have here, basically, I kind of use the amount of stuff in a unit of volume, okay? And the equation we use is density equals mass over volume. And our units we get is grams per milliliter or grams per centimeter cubed. And remember, 1 milliliter equals 1 centimeter cubed from our measurements lecture. And this is why we can use either one of these, okay? The biggest thing is density and mass have what we call a directly proportional relationship. It means they're the same. It means if density goes up, mass goes up. If density goes down, mass goes down. So pretty much I always say they're like twins. When one goes up, the other goes up. When one goes down, the other goes down. So that is a directly proportional. They match, okay? They are the same. They are twins. Density and volume have what we call an inversely proportional relationship, or they're opposite. If you remember from math, the inverse of 2 would be 1/2. So they're flipped. They're opposites. So when density goes up, volume goes down. And when density goes up, or when density goes down, volume goes up. So they're opposite. So you can plug in some numbers and play with this and see that it does work, okay? But these are some relationships that are really important that I want you guys to kind of get. And I'll keep saying these over and over. All right, this is what I call my density triangle. This is to help you so you don't have to do the math when you're figuring out not only density, but say you have to figure out mass. And you don't have to rearrange the equation. And I'll show some of you how to do it if you'd like to know, but this is an easy way of doing it. So what I want you to do is you're going to cover up the value you want to find. So take your finger and you're going to cover up density. So I want you to cover up this D. And if you cover up the D, you can see that D is going to be mass divided by volume. So this line here is divided. If it's across like this, it's going to be multiplied. So mass divided by volume. Say you wanted to find the mass. So go ahead, take your finger, cover up that M, and it's going to be density times volume. That's how you're going to find mass, okay? So you can use this. It's going to be on your homework tonight. So if this helps, instead of algebraically rearranging the equation, you can do it this way, okay? All right, so here's some examples. A rock has a volume of 2.71 milliliters and a mass of 0.650 grams. Find the density. So remember how I told you you needed to know that this would be your volume because it's in milliliters, and you know this is mass because it's in grams. This is what helps. So density is going to be 0.650 grams divided by 2.71, and it's going to give me a density of 0.240 grams per milliliter. The second one is the density of a liquid is 2.66 grams per milliliter as a volume of 31.9 milliliters. Find the mass. So you can use your triangle. You're going to cover up the M, and you're going to see mass equals density times volume. So mass will be 2.66 grams per milliliter times 31.9 milliliters, and it'll get you 84.9 grams. It's a mass, so you would have grams, okay? All right, so this is what I want you to do now. I want you to go back and process your notes. You're going to highlight important information and underline vocabulary words or unknown words. You're going to write down any connections you have with the notes in the left-hand column. Then in the end, you're going to use all that to write a 2 to 3 sentence summary using the processing you did above. And you can go longer than 3 sentences, perfectly fine. When completed, turn in completed notes to the Google Classroom assignment. Okay. Tonight, you are going to do a density and experimental error worksheet, which is another video after this one that you can watch. It is going to be due our next class period. And then you can also watch the video of me doing a density column demo. If you have any questions, please do not hesitate to get a hold of me. Have a great day.